I think we are ready. Sweet. So, last class we left off with this problem about the marginal analysis of revenue. And I kind of skimmed over a point that I wanted to come back to. This idea of revenue, what revenue is X times P. All right, cool. Well, what the hell is X and what is P? X represents the number of products being sold. P represents the demand function. So it's the price as a function of the number of products sold. Make sense?
Yeah.
So when you find revenue, revenue is going to be the number of products you sell times the price you're selling those products at, right? That makes sense. So in this problem, the mistake I had made initially was I didn't calculate what revenue was, right? I just did everything initially on the price. And then I went back and I fixed it because, oops, I realized the mistake. Or I flipped to the next page and then caught the mistake, right? So if revenue is equal to demand times price, well, we're told what the demand function is. P here was equal to 400 minus X for X between 0 and 400, right? Which we then worked out, said, all right, cool, this is 400X minus X squared. And then we were going to find things like change in revenue, dy, or in this case, dr, delta r, I mean to say. And this was revenue at X plus delta X minus revenue at X. And then dr, which is equal to the derivative of revenue with respect to X times dx. And we said we can approximate dx using a small number. This is what we had worked with last class. Jumping really quickly to the next slide, just so we can refresh on what everything was. This term here, d dx of r, that is, again, the derivative, which we find here. Then from there, we said let dx be approximated with delta x equal to 1, and let x be equal to 149. So we're saying, all right, we're selling 149 units, but what if we sold one more? The differential, like I said, isn't actually equal to delta x. We're saying that we can approximate it with delta x if delta x is small. And we're saying delta x is equal to 1. In that case, what we see here then is going to be dr. And what we see here, well, that's what I wrote up top, right? So just to review where these two terms come from. We had said that the change in y let me step back even more. Given that our function f of x is equal to y, the change in y then is equal to f of x plus delta x minus f of x, and dy is equal to the derivative of your function times some differential of x. This is where all this started. So in relation to this problem, what we've got is instead of y, we're working with r, right? And this thing's a function of x because p is a function of x and x is, well, a function of x. So x times a function of x is still a function of x. So x times p is playing this role of f of x, and r is playing the role of y here. Make sense? And in that case, these equations just turn into this. Is everybody cool? Yeah. And like I said, we worked through it and found all of this. Some more on marginal analysis. Let's say we have a profit from selling X number of units, and we want to work out what the marginal analysis is for profit. So we want to find out the P sum. What are we going to do here? How are we going to solve this problem? We want to approximate the change in profit using dP. And then we want to compare it to delta P. Well, first, this is already the function we want to work with, right? So we're going to have to take the derivative of that. So working this all out on the board. We've got P is equal to a stupidly small decimal, 0.0002 x cubed plus 10x. To find dP, well, we're going to have to take the derivative with respect to x of our function for p and multiply it by the differential x, the differential of x. Well, this problem goes on to tell us that we want to approximate the change in profit when we change from 50 units to 51 units sold, or produced rather. So this tells us that x is equal to 50 and delta x is equal to 1. And this is approximately equal to our differential of x. So what are we going to do from here? Well, the first thing we're going to do, we're going to take that derivative. d dx of p is equal to 0.0006 x squared plus 10. So now we're going to multiply this by dx. And we said we can approximate dx as being equal to 1. So dp is equal to 0.0006 x squared plus 10, that quantity, times 1, which is just equal to 0.0006 x squared plus 10. And at x equal to 50, at x equal to 50, this is going to come out to be dp is equal to 0. That's a 0, not a whatever that looks like. 0.0006 50 squared plus 10. So what's 50 squared? Anybody know? It's 1,000 times 25. It's 25,000, right? Plus 10, it's going to give us 25,010. Everybody agree? Want to check my math? Well, my mistake. 0.0006 times 25,000 plus 10. What should say?
Yeah, 11.5.
11.5. That sounds right. 11.5.
That's what I got.
Okay. So we found dp. dp is equal to 11.5. Now, the next thing we need to do is to find delta p. This is going to be equal to p at x plus delta x minus p at x. So we come along. We come along and we say, all right, we've got p plus delta, or p of x plus delta x minus p of x. Can we reduce that any? We could a little bit. Is it going to help us a whole lot? Not by much. But let's do it anyhow. P of x plus delta x minus p of x. This is going to be equal to 0.0002 x plus delta x cubed plus 10x plus delta x minus 0.0002 of x cubed plus 10x we can reduce this just a little bit without going too crazy here to 0.0002 x plus delta x cubed minus x plus 10 delta x. I'm going to say 10 x cubed here. So I reduced a little bit. I cleaned it up some. So now, working this out, since we're evaluating from 50 to 51, we've got P of 51 minus P of 50 is equal to 0.0002 51 cubed minus 50 cubed plus 10. Right? Because delta x is 1. So all I've done here is I went ahead and said if x is equal to 50, add 1 to that, you get 51. Subtract p of x, well, that's just p of 50. So plugging everything in now. Get this. So I don't know what 51 cubed is. I'm gonna type that into my calculator here really quick. 51, the third power, is a stupidly large number. This thing is equal to 0.00002132651 minus 50 cubed. $12,500, $12,500, cool. Plus 10. All right. So does somebody want to calculate that for me really quick?
I have 11.53.
11.53?
Yeah.
That sounds close to right.
I got 11.53.
11.53, all right, we have two saying 11.53. All right. So what is it we're actually seeing here? What is it we're actually measuring? Well, this P of X plus delta X minus P of X, that's delta P, right? And what delta P represents is the actual change in profit. And what dP represents is an approximation along your tangent line, right? So dP comes out to be 11.5 and delta P comes out to be 11.53. In other words, the approximation is undershooting by only about 3 cents. That's a pretty close approximation, right? Since the actual change is 11.53, this is only off in the negative direction, which isn't a half bad thing, right? If you're estimating what your profits are going to be, you probably want to underestimate, not overestimate, right? And comparing it to the question of, will you gain profit exceeding $11? Well, yeah, you're going to gain 53 cents more than that. So looking at their solutions, they calculate the marginal profit, which, like I said, I think it was lecture 4 or 5, DP, the differential of profit, revenue, or cost will be the marginal profit, the marginal revenue, or the marginal cost. So the marginal profit is just this derivative with respect to X of profit. That's what we calculated right here. Everything's looking good so far. We said that X is equal to 50. Okay, looking good still. We said that DX can be approximated with 1. And we got $11.50 just like they did. Now looking at the actual change in profit, comes out to be the same. Comes out to be almost the exact same. Just like what we got, $11.53. Notice they didn't go ahead and reduce some of the algebra on themselves. I do that mostly because, well, when you compare what we've got here to what's on the board, if we had to do this calculation a whole bunch, it'd be a lot quicker to work with what's on the board, right? But if you're only doing the calculation once, this is the quicker route. So just something to be aware of. If you're using the same function, reducing the math a little bit helps you when you have to keep doing that calculation over and over and over again. So something else to notice, this here is our profit function. Notice that it looks pretty damn straight actually. It looks almost like a straight line. And that's why delta P and dP are so close to each other, is because this is nearly linear. So one way to gauge if your function is approximately linear in the interval that you're looking at is to go ahead and do these sorts of differential analysis. You're like, all right, how far off is our function from the tangent line itself? Cool. Does this make sense what I mean? Yeah. Awesome. Good, good. Okay, so some things to know about differentials. If you want the differential of two functions multiplied together, uv, then you're going to have to take the derivative of u times v. But this here, this is just going to be the product rule, right? That's what we're going to apply here. So the differential d of uv, once you apply the product rule, it's going to look like this. It's going to be the u times the derivative of v with respect to x times your differential of x plus v times the differential of u, or I mean the derivative of u with respect to x times the differential of x, which mathematicians will abbreviate using this notation. Something to be aware of, these dx's do not actually cancel each other out. This doesn't actually cancel each other out. This is just shorthand notation. Make sense? So, in the event that you want the differential of two functions multiplied together, you're going to use the product rule to find that that differential is one function times the derivative of the other times the differential of x plus the other function times the derivative of that first function times dx. Everybody cool with this? Having said that, the point here is that differentials, well, you're going to have to apply a lot of your same derivative rules. In fact, you're going to have to apply all of your same derivative rules. So this is page 49 of week 7 notes, just for reference, so y'all can come back to it later if you want. But chugging along, some things to be aware of. Let's say we have a function y is equal to x squared. Well, that derivative is 2x, so the differential of y is equal to 2x times the differential of x. And the same rules apply over and over and over again, right? Nothing's too shocking here. Nothing's revelatory. We're just applying the derivative rules as we should. So what is it this differential is really measuring? It's measuring error of some sort. Error in the tangent line, error in your measurements, error in some way, shape, or form. I had shown this example briefly last class, but didn't really talk about it. I just wanted to present it as one example of somewhere in the physical world where this shows up. In this problem, what we're going to do is we're going to figure out how far off our measurement might be. So imagine you're an engineer, you're building a plane and you need a particular ball bearing. You know there's there's error in the measurements of your tools, right? No two rulers have the exact same error. One ruler might have an error of 0.3 centimeters, another one might have an error of 0.2 centimeters, right? But the point here is that there is in fact error in your measurements. So everything from that point on has some level of error associated with it. This allows us to figure out what that error is moving forward. Is everybody cool with that?
Yeah.
Cool. So in this case, we've got this ball bearing that is 0.7 inches. Seriously though, we do need like self-erasing boards. Just needs to be like a huge etch and sketch. That's what I need. That would actually kind of be dope. All right, so we've got this ball bearing that we measure to be 7 inches in radius. .7 inches, or 7/10, because I would prefer to use fractions. So we know the volume of a sphere is equal to 4/3 times pi r cubed. And just like this problem tells us, it tells us that our sphere is approximately 1.4368 cubic inches in volume. How much can we trust that though? If the error in our measurement of radius is off by approximately 0.01 inches. This is how much it could be off by. How much can we trust that volume to be the actual volume of our ball bearing? What do y'all think? What are we going to do here?
So the volume could be increased or decreased based on whether it is off
Yes.
to that 0.01 inch.
Right. So what are we going to do then?
You smudge some numbers and make it fine.
Okay. But what? What's the process here? Just to show what actually happened. We have a caliper that measures this.
You measure it.
So the process here is going to be using the fact that delta R is between negative 0.01 and 0.01, right? So like you said, it's going to be above or below. So we're going to assume that delta R is equal to our differential. We're going to say, all right, we know this volume. Cool. From here, that means we know dV dr, right? This thing's going to be 4 pi r squared. So dr, dV is going to be 4 pi r squared times dr. Agreed? This should be plus or minus. Let me write it a slightly different way. Negative 0.05 inches. So what are we going to do? Well, the possible error is how far off we could be, which means we need to know plus or minus what dr is, dV is. So this is going to come out like the slide says, to plus or minus 0.0616 cubic inches. Okay. What does that tell us, though? Like, what does this actually say? What this is actually saying, and this is the reason why I wanted to show this problem in this way and kind of walk through it like this. It's because we've already seen how to calculate dr and dV and all of these things a couple of times now. But the interpretation is important as well. What this is telling us is that the actual volume of our sphere is going to be 1.4368 plus or minus 0.0616 inches cubed. So whenever you see something in science or engineering or what have you that's like, oh, this is the answer plus or minus a thing. This is part of what they're doing. They're saying our instruments are accurate up to this. So given that, and given what we think the answer is, based on what our measurements were, what's the range of possible values? Well, in this case, it's going to be that. And if we were to actually calculate it, we would find that the range could be somewhere in here, plus or minus, like I said.
I have a question.
Yeah.
How did they calculate, they said about, like up top, the possible error when the volume is, no, not that far up top, not that far up top. Possible error, plus or minus 0.0. How did they get that number?
So that number comes from the fact that dr can be positive 0.01
Yeah.
or positive 0.01.
Yes. So I tried to plug that into my calculator as just plus 0.01, how do you get the 0.06.6? Like, how would you say, should I just input that into my calculator
So
as 4 pi 0.7 squared plus?
the way I would do it would be 0.7
Mm-hmm,
squared
okay,
times 4
okay,
times pi times 0.01. And now
Okay.
here they round it up.
okay, I'll put it in again. So I just need to break it up when I put it into the calculator, I shouldn't put it in all at once.
Yeah.
Okay,
So for the folks at home, the question was how to type this in and get the result that's expected, that's correct. And the general process is just going to be, first start off with that square. You can't see me pointing because the camera's not set up. First, start off with this square here, right? Then multiply by 4, then multiply by pi, then multiply by your differential. And that'll come out to be what your actual answer should be, right? In this case, they approximated it, hence the way equal signs, that's what that means. And after you do all of this, it approximates out to that. Does that help? Does that answer your question?
I think so, but I think I just keep getting it wrong. Give me a second.
It might be a rounding error in your calculator.
Well, mine keeps going, so mine keeps making it positive before I do the plus. Oh, wait, times it by, give me a second. I got it.
Okay,
I just
cool.
was looking at the answer too early.
Cool. So in either case, because this is plus or minus, we should have plus or minus down here as well. So you can just multiply it by the positive case to get both the positive and the negative case, because they're going to be the same thing, just signs are flipped. Folks at home, does that make sense? Does all of this jive?
Yes.
Cool. Awesome. So something that's commonly asked in science courses would be, what is the percent of error? And what you would do is you'd say, all right, given what dV is, dividing that by V, we're going to get plus or minus 0.0429. This is the percent error not multiplied by 100. So multiplying this by 100, we get the actual percent error. So this is only off, this measurement is off by at much 4.29%, which isn't half bad actually. Having said that, we have hit the end of week 7 notes. So I'm going to pull up very quickly week 8 notes. Give me a second here. Download those. So I'm going to click, that is. Now I'll go back to Zoom. Click on that. So share screen. All right, we just went through all of that. We are now in section 4.1, at which point I want to make an announcement about the exam. The exam is going to be bundled. We're taking exam 2 and 3 and bundling them together. So you're not going to have 4 exams, you're only going to have 3 and the final.
Oh, your gosh.
So
Sorry. I was yelling at the same time.
exam 2 and exam 3 will be bundled together. That means exam 2 is going to end up covering all of your derivative stuff. all the way through. Cool? What's up?
Does that mean it's going to be 22 questions?
Your exam? No way. No way. No, no. So for those of y'all at home who didn't hear that question, it was, does that mean the exam's going to be 22 questions? Yes, absolutely. I'm just kidding. No, no, it will not be 22 questions. It'll be the same size. What it means is you're going to have about 3 questions from every section, right? So this is going to cover chapter 2, chapter 3, and chapter 4. 2, 3, and 4. You're going to have about 3 questions from each of those. Aside from that, what else do I want to say? It will also be next week.
So next weekend?
Yes. And a big chunk of the reason why is because this next section is not largely, it is entirely over exponentials and logarithms. And as a result, we're really just going to ultimately be talking about something from algebra and then throwing the derivative on top of it. That means it's pretty much an extension of everything we just talked about. And in my mind, in this particular format of the class, it doesn't make sense to break it up. For the sake of time and exam prep, I'm going to bundle the 2 exams together. If I do end up making this exam a little bit longer than 9 questions, you'll also have more time, right? And part of the reason why that might happen is because in chapter 4, when talking about exponentials and logarithms, there are questions other than things pertaining to the derivative that I think I should probably test y'all. So if I do extend the exam at all, 1, it will certainly not be 22 questions, right? 2, I will also extend the time that you have to take the exam. Because that's only fair. If there's more questions, more time. Having said that, let's get into this section 4.1. Sorry for the timing on that.
Oh, no, you're fine.
So the first part of this chapter is just going to be talking about exponential functions and what they are. An exponential function takes the idea of x raised to a power and flips that. It's a value raised to x. So now, instead of the variable being your base, your exponent is your variable, and your base is a constant. Cool. And this is something we're actually all already familiar with. Anyone who's ever looked at by a computer may have noticed that computers come in a handful of different hard drive sizes. They usually start off about, give me a second to remember this, 64 gigs, 128, 256, so forth, so on. Well, what are these? This is 2 raised to some power. This is 2 raised to another power, and 2 raised to another power, right? This is 2 to the 8th, correct? 2, 4, 8, 32, or my mistake, 8, 16, 32, 64. So 2 to the 6th power. Yes, I just did that on my hand. That is a totally acceptable way of doing calculations. Keep track of your work. Use whatever utilities you have, whatever resources. But if that's the case, then 128 is 2 raised to the 7th. 256 is 2 raised to the 8th. And what we find then is that hard drives are defined in terms of 2 raised to some power. Let's call it N for right now. And I'm calling it N just because we go over integers. But we can generalize this to any number for a power. And this is an example of an exponent that we've all seen. So what an exponential function is a base greater than 0, not equal to 1, raised to some variable power of x. 2 is greater than 0, not equal to 1, and it's raised to some variable power here, right? So just a couple properties of exponents that we should already be familiar with from algebra, but just as a refresher to knock off some rust. Any value raised to the 0th power is always equal to 1. The product of any two numbers with the same base but different exponents is that base raised to those two exponents added together. Division is the same idea, except now it's the subtraction of those two exponents. A base raised to a power, that quantity raised to another power is equal to that base raised to the product of those two powers. If we have two different bases multiplied together and raise them to a power, that is equal to one base raised to that power times the other base raised to that power. Similarly, division. And any negative power is going to give us a fraction, right? So I'm not going to spend a whole lot of time on this section because I think we already, for the most part, know this stuff. But as a couple quick examples, 2 to the second times 2 to the negative third can be calculated in a couple different ways. We could say this is 4. This is 1 over 2 to the third, which is equal to 2 to the 8th. I mean 1 over 8, right? So 4 times 1 over 8 is going to be equal to 1 over 2, right? Or we could say, hey, these two bases are the same, so this is equal to 2 the second minus the third power, right? Which is equal to 2 to the negative first, which is equal to 1 over 2. So we could approach these problems in a couple of different ways. That's really just all I wanted to show here. Having said that, looking at this last example of f, 2 to the 1/2 times 3 to the 1/2 could be rewritten as 2 times 3 raised to the 1/2 or 6 raised to the 1/2. Or we could rewrite it in terms of radicals. Is there anything else I wanted to show here? That was it. Awesome. All right. That's it. So now, just a couple more examples of using exponentials. When dating, when doing things like carbon dating, what we're looking at is the presence of radioactive isotopes of carbon. And this idea here is that different elements decay at different rates. Decay is an exponential function. And because of this process of decay within the isotopes of different elements, we can say the presence of one type of element compared to the presence of another type must mean that the one type has been decaying for this long. So what they're doing is they're looking at different isotopes of carbon. I think it's carbon-12 and carbon-14 that they're comparing. And they're saying, all right, naturally occurring, there's only this much carbon-14 or this much carbon-12. One of these two will have to decay. As it decays, because the natural presence is a certain level, you'll be able to say, we can use this new amount, say this is how long we've been decaying, based on what it should have been if the thing just died today. Does that make sense what I mean? Kind of, sort of? Yeah. So this is an example of that type of a problem. And all they're really asking for here is for us just to calculate what the ratio of carbon isotopes should be at different times. So plugging in 10,000 for T, 20,000 for T, 25,000 for T. And what this value 5,715 is the half-life. This is how long it takes for half of the isotopes to decay. So if you have 1 gram of carbon-12, it takes 5,715 years for half of it to decay, so that you only have half a gram of that original isotope. That is where this 1/2 comes from. And this is a relationship of the quantity of isotopes. For every 1 isotope, you should have 10 to the 12th of the other isotope. Does that make sense what I mean? Is everybody cool with this? We're going to be talking more about like these types of equations after a while when we get into modeling with exponentials. The point here is just to say, yeah, you're just plugging in the values. You have a variable as an exponent. You want to know what that calculates out to be at a certain value. So a certain value in this case for T, just replace T with that value. Cool. So a new question then shows up. What about graphing these things? What do these graphs generally look like? Well, we've already seen 2 to the x. That thing grows, right? And it makes sense that 2 to the negative x, this thing is going to shrink. Agreed? So just really quickly checking these out. We can approach this question by just writing out a table and saying, all right, at different x values, what do these things calculate out to be? And then graphing them. And we find a trend. Notice with positive x values, we have a function that grows. With negative x values, we have a function that decreases. So positive x values growing, negative x values decreasing. Something particular is happening here. It's not that it's the positive x or the negative x that's making it grow. It's that your base is less than 1 or your base is greater than 1. And I say that because notice 1/2 to the x power, well, that's equal to 2 to the negative x. So you don't have to write this in terms of a negative exponent. You can write it in terms of a positive exponent. And when you do, you get a base that's less than 1. And that brings us to some general trends of what happens with exponential functions. Given that a is a constant greater than 1, if your exponent is negative, you're going to have a decaying function. And that's assuming that your base here is greater than 1. And it's going to have all these different characteristics. These are some things you should know I'm not going to quote them all back to you because, well, parroting off slides sucks for the students, I know. On the other hand, given that a is greater than 1, a positive exponential value is going to lead to something that grows. Now, there's something to note about both of these functions that is very, 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 very important, very useful, frankly. Any base raised to a power will always have to be equal to 1 when that power is 0. So if you have a base raised to some exponent, when that exponent is 0, it's going to go through 1. So long as you have some base raised to negative x or some base raised to x, you're guaranteed that your graph is going to go through 0, 1, 0, 1. However, if you had, say, pi out front, so this was pi times a raised to the negative x, then this thing would become 0 pi. Cool? You're just multiplying 1 by the constant pi. Does that make sense?
Yeah.
Folks at home, are you following me on that? Does that make sense?
Yep.
Yep, cool. All right. Well, what about when we subtract values? What if we have functions that aren't just exponents? Well, this behaves just like any other function. If you're going to subtract a constant from a function, so we can start off by saying g of x is equal to 3 raised to the negative x. So f of x is just g of x minus 1. And the only difference between the two graphs would be that f of x is shifted down by 1, right? So what I am saying is this. It's negative, so it's decreasing, wasn't it? Yeah, it's negative. All right, let's say this is the graph, g of x equal to 3 to the negative x. Then our function, f of x, is going to be the same exact graph, just shifted down by 1 unit. That is because this is the point 0, 1. That means this is the point 0, 0. Now, we could go about this by creating a table and then graphing it if we wanted to, and checking what happens in all of these limits. We could do that because we know the general behaviors within the limits, and we know the general behaviors of how functions change when shifted by constants, right? So having said this, I think it is time for a nice little break. Give you all about 10 minutes. And we'll come back to section 4.2. So be back at 7:20.